Hello and welcome to Post-Media Time Talks. We are part of the Young Academy and we welcome you to the last session of Post-Media before summer. Today we have two interesting talks from two wonderful speakers. If you are interested to present or be in contact with Post-Media Time Talks, and send us an email, we will be in contact with you. With that, I would like to introduce our first speaker. Our first speaker is Simon. He has an undergraduate degree in geology. And he graduated in environmental sciences in 2020. He joined the Hyperborea project during a 6-month internship in early 2020, and he pursued through the thesis. Simon currently is at the end of his second year, and he teaches geochemistry and sedimentology at an undergraduate level. Thank you, Simon, for joining us today, and the floor is yours.
So, hello everybody, my name is Simon, as introduced. I'm the second year PhD student at the Toulouse Institute of Geomechanics, and I will present you today my work done at here. So, it's about the uncovering of the hydraulic and thermal properties of Arctic lichen, moss and peat from permafrost dominated catchments. Sorry, up, come back. And we are doing that through numerical studies. So this is work done here and in collaboration with another lab in Toulouse, Geoscience Environment Toulouse, as well as 3 other labs in Russia. So before going deep into the details of permafrost and, well, the hydraulic and thermal properties, I would just briefly introduce you the permafrost dynamics and the conjunction with the Arctic biomes. So basically, permafrost is a soil layer that is permanently frozen for at least 2 consecutive years. So this permafrost is covering mainly a fourth, like 25% of northern hemisphere continental surfaces, as we can see on the map here. Well, you can't see really the permafrost by itself because it's under the soil, but if you look at some erosion fronts that we can see, for example, in eastern Siberia or in Alaska, we can see that this soil layer is containing ice, and in fact, more precisely, there are 3 main layers in this permafrost. You have the uppermost layer, which is the active layer, which is thawing each summer because of the positive temperatures of the atmosphere, basically. And then you have this layer is 1 meter thick, approximately. And then you have what we call the isothermal permafrost, which is a layer where the ice is perennial. We don't have any thaw or any melting or whatsoever. This is the permafrost on its own sense. And then this layer can make from 1 meter to 1 kilometer thick. And then below that, we have the frost-free soils, and the frost-free soil is in fact the soil that is always melted because of the geothermal gradient. In these particular regions, the main energy driver and where the fluxes happen is in fact through what we call a cryptogamic layer by the mean of evapotranspiration. But so what is the cryptogamic layer? The cryptogamic layer, in fact, is a complex patchwork of some vegetation and some symbiotic association with fungi, algae, so respectively sphagnum moss and lichen. We can see some landscapes here, so it's a complex patchwork which is of low height vegetation. And these two particular structures, so lichen, which is not in fact vegetation, and sphagnum, are known for their high retention capacities because they don't have, well, the lichen obviously no, but the sphagnum neither. They don't have any kind of particular structure that allows any conduction of sap conduction. So they are in fact obtaining their water or fulfilling their water need only through capillarity. And this capillarity is done thanks to the hyaline cells. So you can see on the right here the hyaline cells. They are all the small gaps for example, in the sphagnum leaf. And these hyaline cells are in fact keeping the water into the plant. And you have the mesh there, this kind of grid, which is chlorophyll and which is doing the photosynthesis. And so the plant is getting the energy through that. So why that? Because in fact, this cryptogamic cover is exposed to climate change brutally, and the Arctic regions are, you might have already known through the newest IPCC report, that these regions are the regions that are warming the fastest on Earth, with some 0.4 degrees of increase for the continuous permafrost and 0.1 for the discontinuous one. And when you check some Earth system models, for example, the GS-BAC model, which was made by Porada and his associate in 2016, we can see that if you don't take into account this cryptogamic cover, which is represented here in the graph by the bryophytes and lichen curve in black, we can see that we don't have at all the same same answer of temperature if you take here a thermal conductivity for this layer. So in fact, this cryptogamic cover is very important in the assessment of the climate change impacts. So we need to assess these hydraulic and thermal properties of this layer. But how we are going to do that is, in fact, in the framework of the Hyperborea project. So we are putting high performance computing to quantify the climate change impacts on boreal areas. And we are doing that for various climate change scenarios. You are already maybe familiar with the 1 plus 1.5 scenario plus 2.3, what we call in the media. And we are doing that with a new approach because we are considering this structure, this cryptogamic cover, as a porous media. So that's why it's linking with the porous media sciences. So we are in fact collecting samples. We have 2 study sites on this project, which is Hanime in Western Siberia, shown here, and Abisko in northern Swedish Lapland, here. And we have already collected in 2018 12 samples, which of 8 samples of sphagnum, 2 of lichen, and 2 of peat. And then we are going to collect this summer, so the next month, some new samples from Abisko. And how we are going to study these samples, in fact, we're doing this with a couple experimental and numerical setups. And these setups, in fact, are used for the first one to reconstruct. So to reconstruct the porous space, we're scanning our samples, which are of approximately 10 centimeters of edge size. We're scanning you through the X-ray computerized tomography system, which we have here at the Toulouse Institute of Field Mechanics. And we are getting a reconstruction with a precision of 94 micrometers per voxel. And finally, we are also doing a thermal camera acquisition chain, which is in fact helping us to get the thermal information. So we have these 2 experimental setups. We have also, which are coming from them, 3 different numerical setups. I already introduced one, which was the reconstruction, but we also made a simplified model of this porous media, which you might already be familiar, which is the pore network model, so PNM. And finally, we made a kind of a continuum approach where we make a mesh and we apply some properties on this mesh. So here, the hydraulic properties were studied with numerical setups because we didn't have the numerical setups. We scanned them, but we mainly do that. And for thermal properties, we aim at coupling these experimental and numerical setups to, in fact, intervalidate them furthermore. So if you go on the hydraulic properties, we have first, I didn't mention it really, it was really outside, but we've studied the representative elementary volume of these samples and we based it on porosity. So basically all the samples we studied were highly porous and some of them were sufficiently homogeneous to allow us to use direct numerical simulation on them based on this representative elementary volume. And using this RAV, we can then find a hydraulic conductivity tensors. Here I averaged them for the sake of simplicity because it was going to be quite complicated otherwise. And we can see that these hydraulic conductivities are very high, with 1 centimeters per 1 centimeters per second to 1 meters per second. So this is hydraulic conductivity. We can also talk about permeability, intrinsic permeability, which is in fact what we found, and it is ranging between 10 times 9 to 10 times 7 square meters. And for the least homogeneous samples, we used the porous network models because we couldn't in fact do the simulation on the wall sample. It was too much of a burden in terms of computational resources. So this was the hydraulic properties, and now we are studying the thermal properties. In fact, the hydraulic properties I forgot to mention. We have submitted a paper which is now ongoing reviewable, and we're waiting basically the review. So for the thermal properties, we are using this infrared camera. So the camera has a resolution of on our setup of 108 micrometers per pixel. So it's basically the same as we got for the X-ray tomography system. And we have first done a kind of setup where we warm the sample through under it, and we put some insulating material on the sides, which is polystyrene and glass wool to fill the gaps, because the samples are not really a little bit rugged, so it's complicated to get the perfect airtight system. And we put some thermocouples inside and heat flux sensor, and we image it on the top, and we get the results we have here. So we can see that I just put the sphagnum because lichen and peat was a little bit more complicated to interpret for now. So I only mentioned the sphagnum for now. And we can see that we have, in fact, a thermal image that is very contrasted with the uppermost structures that are in fact at ambient temperature. And on the sides, it's nearly the heating of the plate. So we have also the picture there, and we can already see on all those results that we might have strong isolation properties. That has been also already found in the literature, and perhaps low thermal diffusivity. So the quantification of the thermal diffusivity, thermal conductivity, and capacity, calorific capacity are to come. And finally, before going to the outlook, I would just mention what we have tried just last week, in fact, which is a new setup of thermal properties assessment. And here we wanted, in fact, to counterfeit all the problems that we have on the boundary conditions, because when you heat from the bottom, you might have a lot of natural convection that is occurring, and this is very more complicated to post process if you want to get some properties. So we wanted to do another setup where we warm it from the top, so we don't have this convection occurring, or we don't care. In fact, it's going up, and we are seeing only conduction. And we put the camera on the side, so on the horizontal plane, so we can see. We wanted to see the thermal gradient that is in fact occurring during the warming. And if we do that, we can already see on the picture. So I colored some thermal fronts to see how it propagated, and this is the result I got just a few days ago. So it's very fresh, it's very preliminary, but we can see that this heat front is kind of propagated through the sample in a way that we have seen also on the simulation. So we might here get more information for the thermal properties than on the other one, because the other one was very complicated to really post process. We couldn't do anything. So better boundary conditions and more in the actual temperature gradient. That leads to the outlook, which is the coupling with the simulation. So here we made a small simulation. In fact, it's where the continuum approach enters, because we had this problem of importing our reconstructed sample into a simulation tool, which is OpenForm, and we couldn't import it as is because it was too big. So we decided to just crop it and use the continuum mesh. So just creating a mesh and applying some thermal diffusivity. This is what we have already found in the literature. So it just was a test. And we found that we had a plus 10 degrees difference on one altitude, one Z, I would say. And this is what we have also seen in our first setup with the thermocouples. If you remember, we had the thermocouples like a brush inside the sample, and we had a problem because we can't know where is the thermocouple. We could scan it, but it's very complicated to scan because we would have some artifacts that wouldn't help us, so it would be very complicated to see. And with that, we are trying kind of correlating already the results that we saw on the first setup, and we are now aiming at correlating them on the new setup. But it's so fresh that I definitely don't have no results yet. And finally, this is maybe the most complicated part, which I hope I will be able to do it during my remaining of my thesis, is to couple these properties with water saturation. So we want to saturate with different rate our samples, and to do the same to get some hydraulic and thermal properties for these porous media with various saturation, and to see how the water is in fact occupying the pore space, because there's a lot of literature that's telling us that really the water height in this sample is very important for all the natural dynamics, but there's no really some porous media assessment yet. So we would like to do that on the next step. So I hope that you enjoyed my presentation, and if you have questions, please feel free to ask.
Thank you, Simon. Thank you for this interesting presentation. It was really fascinating what you are doing in this project and the tools that you are applying to study properties. Would you please explain for us more about the basic properties that cause these differences in properties, in thermal properties that you measured in the lab? And can you differentiate between the matrix properties and the properties that are associated with the heterogeneities in the porous medium?
Well, it's a bit complicated to dissociate them, but at least for the first setup, it was very complicated because we just see it from we looking down. So we are not. It's very complicated to see what's happening inside the pore themselves and just what is happening on the surface. Now we might see it better on the side, because we can differentiate quite well what is pore space and what is the matrix. Because when we look at on the up, we had the problem of perspective. We couldn't know really what was on the top and what was at what altitude and so on. But now we might be able to differentiate. But this differentiation will happen through image processing, basically.
And what do you think about the differences between the material that you tested upon in comparison with, say, ordinary soil or porous rocks? You see any difference from the literature?
In fact, one of the main difference is that these are living biologically active porous media. So of course soils are biologically active, but they are not active on their own. They are active because they are bacteria or bioturbation or things like that. But they are like living organisms. And more precisely for sphagnum at least, in fact, each leaf or each branch is an individual. So when we talk about sample, we might talk about hundreds of individuals which are forming a colony. So this is the particularity, because in fact they are making the porous media. The sphagnum individuals are making the porous media, and not kind of physical degradation, weathering, or things like that. So it's much harder than to correlate, because as it is living, it grows, so it changes over time, and and it's really adapting it to its own environment. For example, I'm growing them now on the lab, and if you change the water saturation for them, they are really changing their pore space. If they have a lot of water, they are really far apart from each other, because there's no capillary pressure needed to get water. But if you reduce the water saturation, if the water table is going lower and lower, then they are coming closer and closer, and then in fact everything changes. Everything changed. I would like to say porosity, hydraulic conductivity, everything. So it's very complicated indeed.
It's so interesting.
And great. And I also want to ask you a question. Actually, it's just a curiosity regarding your saturation experiment. I know that it's something new, but how do you are going to keep this initial saturation condition in the lab as similar as possible to the field saturation? How you're going to keep them similar to
Well,
perform
that's
the
an
experiment?
interesting question. Yeah. In fact, we it's complicated to keep them on the same conditions, because water table is, well, even though it's very high, so they are literally in the water on the field in the field, but we are keeping them in a box, and we can
Okay.
put the water in the box and close it. But
Okay.
the conditions, at least for the water conditions, might be okay, but we might have some problems regarding all the bacterial degradation and mold and everything like that. So this is maybe a more of a sanitary question, maybe. But yeah, we
Okay.
can, for the water saturation, this shouldn't be.
Okay, great. And just as curiosity, to put the number in perspective, are we talking about what, 17%, 80%?
95% porosity.
95, okay,
For
see.
some of them, it's 95. So it's very,
Okay.
very porous.
Yes, exactly. Okay, awesome. Thanks.
I guess we have another question from Marcel in our studio. So Marcel, go ahead.
Yeah, there's one question from me, but maybe we take the one from the audience first. There's one question that just popped up.
Definitely. Okay. First, Trent says thumbs up, clap, clap, clap for your talk. Now we have
Excellent.
another question from Sasmit. Thanks for the talk. I have a somewhat different query. Are you observing any difference in pattern of heat transport with variation in porosity? Is transport reaching equilibrium with varying porosity?
Well, if I understood correctly, if we see, the question is if we see some variation when we between the samples, so between some porosity variations. And yes, indeed, we see some differences, because I showed on my presentation some sphagnum, so what the samples which are the most porous of our sample lot, and we saw that these were not really conducting heat, so the uppermost structures were quite cold, in fact. But if I would have shown the peat sample, which is the least porous of the lot, then we have in fact more homogeneous thermal image with the surface which is on average the same temperature. So yes, we have some heat transport differences, and this we're going to see with the new setup, because with the other setup we couldn't really see.
And do you see any equilibrium in the transport?
Mm, we reach some kind of equilibrium if we heat it for 2-3 hours, but as we had the problem with the boundary condition, we were not really sure whether it was the just any kind of equilibrium with the ambient room, because we had this climatized room, so air conditioned room. So we have this problem also, but we reached some kind of equilibrium. It's to be very confirmed yet, but still, but we might have equilibrium.
Okay, Marcel, now it's your turn.
Right. Yeah. Super. Thanks a lot, Simon. That was really, really interesting. I have two quick questions. One is just something that I didn't understand is one of your images. If you go back to the first image that you show, the thermal signature, I didn't really understand that there.
Yeah,
I
it's
know
coming.
to the right. No,
Yeah, it's coming.
there.
This
Yeah.
one.
Yeah.
Okay.
Exactly. So what's left and right? There is a big boundary in the middle.
In fact, I was not very precise on that. The left side and the right side are two different samples. I just cropped them for just to that it enters in the
Okay.
presentation. In fact, when the G, where is the G cuts, the sphagnum G is cutting both sides, it's two different samples.
Right.
So
Mm.
that's all.
Okay. And so I understand that you have to take care a lot with the boundary effects on these
Mm.
measurements, but because probably what you want is the thermal signature in the bulk.
Yes.
That's what matters for the understanding, for the simulation, and so on. But later on, when you change the boundaries to have like the heating from the top, which is also I think more representative of what happens in nature.
Yeah. Also.
Um, you have like this window from the side, right?
Hmm.
How can you be sure? I mean, like, do you have an indication that there is no heat transfer from through the window, like from the outside through to the surface of the material that you are imaging?
Well, it's something that is. Yeah, it can happen. It can happen.
Mm.
We can have some warming of the window itself, and we have also maybe some leaks in from the outside.
Mm.
But the window is what we found. The fluorine window is one of the best, maybe because it has low thermal conductivity, so it's kept at nearly ambient, and we are having still a small air gap between the window and the sample. It can cause problems, some issues on that, but we found that if we don't stuck it through the window, not the window is not warming up. Because I forgot to mention that on the two plates that we have on the hot plate and the cold plate, we have thermocouples. We have put the thermocouples on them, and for the cold plate is not warming at all. So we assume that there's no significant warming of the window itself. So
Right.
we assume that maybe for the longer times, if we do that for 6 or 8 hours or 10 hours, I don't know, it could really matter. But as we're keeping like 2-3 hours, maybe
Mm.
it's kind of negligible.
Yeah, I also like when you showed like the isotherms in
Mm.
another slide. I think that kind of makes sense with what you would expect from those, right? Like
Yeah, yeah.
so this
We're
kind of indicates
reaching.
also that
Yeah.
things are working. Yeah,
Mm.
that's excellent. Thanks a lot.
You're welcome.
Perfect. Thank you, Simon, for this wonderful talk. Now it's time to move on to our second speaker. Our second speaker is also from the same institution as Simon, from Toulouse Fluid Mechanics Institute in France. Omar has a master's degree in applied mathematics from Sorbonne University, Paris 6, with a strong component in fluid mechanics. Nowadays, he's working on his thesis at the Institute of Fluid Mechanics of Toulouse on a project that is funded by Total Energies. And he will tell us more about the project and what he's doing these days. Thank you, Omar. The floor is yours. And you are muted.
Do you hear me?
Yes, we can hear you.
Yes, I am Omar Mokhtari, a last year PhD student at Institut de Mécanique des Fluides de Toulouse. I am working on the flow of polymer solution through porous media. This is a project funded by Total Energy in collaboration with Michel Quintard and Yoann David. And I will present you today the role of the strands in polymer solution flow through porous media. Polymer solutions are generally used in groundwater remediation or enhanced well recovery, and this is a viscoelastic material with with behavior between viscous and elastic, depending on relaxation time lambda. When the time of solicitation is greater than lambda, the polymer solution have an viscous behavior, and when the time of solicitation is smaller, the behavior is elastic. This can be characterized by the Weissenberg number, which is the ratio between elastic and viscous forces. And as we can see, it scales with a velocity gradient. So in porous media, where the Reynolds number is generally small, we can have high value of this number. To model this flow, we use a dumbbell model, where each polymer is corresponds to a dumbbell with an entropic restoring force. If we define Q as the end-to-end vector, we can introduce the conformation tensor, which is the second order moment of Q, and this represents the conformation of the polymer in the flow. So the flow is described by the Navier-Stokes equation with an additional term here corresponding to the stress induced by the polymer, and a constitutive law here, which is a transport equation of the conformation with a source term here and a relaxation term here. The major difficulty to solve this system is this source term, where the velocity gradient can be very sharp. So this equation is very difficult to solve. So we propose to use splitting of this equation into two terms. The first equation is a pure advection equation on the logarithm of c, and the second one is a local ODE with a local time step depending on the local value of the velocity gradient. So we first consider the flow past a single cylinder. We impose biperiodic condition, and we increase the Weissenberg number. On the left, we can see the trace of the conformation tensor, and by increasing the Weissenberg number, we can see the appearance of a strand in the wake of the cylinder, which increase almost linearly with the Weissenberg number. This corresponds to high elongated polymer, and this polymer acts as a tangential force opposite to the flow. So if we consider the velocity field, for a low value of the Weissenberg number, we have a Stokes flow with a 4-aft symmetry, and by increasing the Weissenberg number, we can see a decrease in velocity in the wake of the cylinder due to the strands, and by conservation, we have an acceleration of the flow around the cylinder. Now, if we consider two cylinders, this is a very interesting test case with at the beginning, due to the gap between the two cylinders, we have a pre-existing flow around the two cylinders, and the flow between the two cylinders is smaller. Because of this pre-existing preferential flow, the trends are curved. So by increasing the Weissenberg number, the two strands go closer and closer, and until they touch. So at the end, we can observe that we have no more flow between the two cylinders. This is a very important mechanism of amplification of pre-existing preferential flow path. And in more complex structure, as disorder arrays of cylinder, this mechanism can explain the flow, the channeling of the flow, with the same effect of amplification of preferential flows and more stagnation zone here. The question that arises is what happened in ordered arrays of cylinder, where by definition there is no pre-existing preferential flow. there is two very recent experimental results. The first one consider hexagonal lattice of cylinders in a staggered configuration. By increasing the Weissenberg number, they observe the appearance of fluctuation, a transition to unsteady flow with velocity fluctuations, and by introducing a disorder, the fluctuation disappear. They say that disorder suppress chaos in viscoelastic flow through porous media. But considering the same geometry, but in an aligned configuration which correspond to a rotation by 30 degrees of the first one, the second study observes the opposite, which is that by introducing disorder, the transition to fluctuation is advanced. So to understand what happened, we solve numerically. We consider numerically this hexagonal lattice of cylinders. We impose a flow through force F with a fixed angle theta, and by we increase the Weissenberg number through the magnitude of F. If I consider, for example, the case theta equal to 25, we can see that the mean velocity angle, which is alpha, decreases until 0. So at the end, we have only two preferential directions of the flow at 0 degree and 30 degree, and we can see that 0 degree is more stable than 30 degrees. To explain what happened, this mechanism can be explained with strands, where in the case of theta equal 25, we have a pre-existing preferential flow on the left of the strands. So by increasing the Weissenberg number, this preferential flow will be enhanced, and the flow on the right will decrease. And we can see by increasing the Weissenberg number, the strands go in an horizontal position. Okay. Now, if we now fix the angle, we fix the Weissenberg number, we fix the amplitude of the magnitude of F, and we increase theta degree by degree. We can see a sticky effect where the strand remain on the horizontal position until theta equals 30, and we have an abrupt drop-off of the strands, and at the end we have a second sticky effect at 60 degrees. We can see we highlight the presence of an hysteresis on the angle theta. By further increasing the Weissenberg number, we can see, due to this coexisting stable state, the beginning of fluctuation. We have a periodic oscillation of the strands around theta equals 0. And by further increasing this sticky effect, we can see that the oscillations are no more periodic, and we have a propagation of traveling waves. So the fluctuations are no more periodic and are around two angles. To understand this mechanism, this can be understood by the two coexisting states: a state where the strands stick on the top, and a state where the strands stick on the bottom, and the wave corresponds to a switch between these two states. Uh, okay. By further increasing the sticky effect, the Weissenberg number, we observe a very complex pattern of the strands, and this pattern is now fixed with small oscillation. Uh, this can be this corresponds to a pulsating regime, where strands where small oscillation around preference fixed pattern. Okay, so to conclude, we have shown the important role of the strands in viscoelastic flows, and that these strands can explain many aspects of the flow through porous structures. A lot of question, a lot of question remains as the role of these strands in the transition toward KO and the viscoelastic turbulence, and in more complex flow as 3D flows, what is the role of dimensionality and so. Thank you, and if you have any question, please ask.
Thank you very much, Omar. That was very interesting. Welcome the audience to add any questions to the comments field on YouTube if you have. I have one for now. So when you showed the hysteretic loop, can you just explain again, like which one is the parameter that you are tuning and which one you are measuring? And could you make the hysteresis loop happen anywhere? Like for instance, now for one of the cycles you stopped in the middle, like alpha around 30. Could you have chosen that line anywhere you wish?
Okay, this loop
This loop, yeah.
Here we only increase, we fix the magnitude of f, and we increase theta, which is the angle of f, degree by degree. So at the beginning, we can see that strands stick on the horizontal position, and by we only increase theta until we observe a drop. So we to understand this this first plateau, we decrease theta around 30 degrees. So we can see that the strands will interact with these cylinders, which explains this plateau at 30 degrees. So now we decrease theta, and now we increase without this plateau, so we increase until 60 degrees to show this second hysteresis, this second stable state. So at the end, we can observe that there is three stable states, three stability. For theta equals 30 degrees, we have three possible position of the strands. I don't know if it's more clear.
Yeah, it is. Yeah, that's very interesting. And there was in another plot before, you said that's the zero, that one there, the alpha 0 was more stable than the 30. Can you just explain how you conclude from this that it is more stable? What does it mean to be stable in this context?
Yes, sorry, I was not correct. It's not more stable. It's in fact there is more angle theta that decrease to 0. There is
okay, it's like the basin of attraction of that 0 is larger.
Yes, exactly. Until 27, the sound will decrease to 0, and we have the final position is 30 degrees for only 3 position.
Right.
So this is yes. Sorry for the.
No, yeah, that's very good. Super. Thanks a lot. That's super interesting. Let's see if there are more questions. If there are not, I still have one more, but maybe we should see. Is there any other question from the audience or from the team here?
Oh yeah, and meanwhile, I want to ask you one, Omar. And have you evaluated the influence of pore space topology in this polymer flow? Because as I can see, there is like a homogeneous distance between these cylinders here.
Yes, this was a very specific study because we have experimental results to understand
Ah, yes, that's true. Yes.
exactly. But we also studied the effect of porosity in other configuration. But I only present here this study because of the experimental results. There is two experimental study with two different conclusions, and to understand what happens, we focus on this classes.
Yes, yes, okay.
Okay, I see we have some questions from the audience as well. So I'll add them up here. Moitaba Nurusi, he says, thanks for the interesting talk. What does the trace of C represent physically?
Yes. Okay. Uh, as I explained, C is the second order moment of Q, and trace of C represents the elongation of polymer. So C is a tensor, and the diagonal term correspond to the normal constraint. So the trace of C represents the elongation of polymers. We can see that. And
Right, and
yes.
then we have another question from Kwame Obusu Eduse. Thanks a lot for your presentation. I would like to know if which hysteresis model you used in your simulation.
No, there is no hysteresis model. It's we highlight the presence of an hysteresis. We don't use any model.
Right. And Maxime Koshenek, very nice work, Omar. Did you use an in-house code to solve PDEs or available PDE solver libraries, example, free
Yes,
FEM or
uh,
none?
yes. I don't. We implement our own in-house code in Caliph 3S, which is a platform open source from IRSN, Institut de Recherche et Sûreté Nucléaire in France. So yes, this is our own code, but it's open source.
So it's open source. I suppose people can find it online.
Yes.
Great, excellent. So if we don't have any other questions, I think we can close the session here. And I would like to thank and congratulate both speakers again. Those were really excellent presentations. I think there was a very nice closing to our session. And this is actually our last session of this semester. And we will start again a couple of months from now. We're still defining a little bit the format and so on that will continue further. But before we finish, I would like to mention that we are now collecting names for potential new team members also for the Tea Time Talk. So always when we finish the presentations, we ask people to send us messages if they want to be speakers or if they want to recommend speakers. And we also ask for that. So we're always building a list of potential future speakers. But also now we are collecting potential new team members. So if you think that you would like to join the Tea Time Talks team, I think this is a very nice opportunity for us to build some soft skills that sometimes it's not so easy to get from the regular education from the university. So I guess this counts a lot. It has been very, very good for me, and I'm sure for many of the others of the team as well. So if you would like to join the team, please send us an email, and we will contact you later on when the positions come up. So our email is porusmediattt@gmail.com. And you can join from pretty much anywhere. So we welcome members from everywhere in the world. In fact, it's very good for us to be very diverse in the world, because so we try to have very many different time zones and like to try to have talks that are available for people all over. So now we have people like Catherine that's on the west coast of the US, and I am in Norway, and there's a bunch of people spread all over. Nara is in Brazil, Sarah is in France. So it doesn't matter where you come from. You're welcome in the team. And if you would like to join us, or if you would like some more information about what we do and how it is, please contact us. And this is porusmediattt@gmail.com. And we will, the next session, it will be advertised on all our channels very soon. So thanks again. Thanks to the Interpor Academy, or part of the Interpor Young Academy. And most of all, thanks to you for watching and for supporting us. Bye from us.